Episode 45, AI Semantic Search at Scale, How Senior Engineers Build Production-Grade Meaning-Based Search Systems. Welcome to Agentic AI World Interview Prep. I'm your host, and today we're tackling one of the most asked topics in senior AI engineering interviews, semantic search at scale. If you're interviewing at companies like Google, OpenAI, Cohere, Databricks, or any AI-forward company, expect this to come up. Let's break it down. Section 1. What is semantic search, and why does it matter? Traditional keyword search, like BM25 or Elasticsearch, matches exact terms. If a user types car engine problems, it finds documents containing those exact words. Fast, cheap, predictable. But semantic search understands meaning. Automobile motor issues, vehicle engine fault, and car engine problems all mean the same thing. Semantic search returns all of them, ranked by conceptual similarity, not word overlap. The secret is embeddings, dense vector representations where similar meanings sit close together in high-dimensional space. In an interview, frame it this way. Semantic search replaces lexical matching with geometric proximity in embedding space. Section 2. The core architecture, 3 layers. A production semantic search system has 3 layers. Layer 1, indexing pipeline. You take your corpus, documents, product descriptions, support tickets, whatever, and run them through an embedding model. Good choices. OpenAI text, embedding, 3, large, Cohere embed, v3, or open source models like BGE, M3, or E5 Mistral. Each document gets chunked first, typically 256 to 512 tokens with overlap. Then embedded. Then stored in a vector database, Pinecone, Weaviate, Grant, or Vector if you want Postgres native. Layer 2, query processing. At query time, you embed the user's query using the same model. This is critical, same model, same embedding space. Then you run approximate nearest neighbor search, ANN, against your vector index. Popular ANN algorithms, HNSW, hierarchical navigable small world, gives you sub-millisecond lookup at scale. Face from Meta is another option for in-memory workloads. Layer 3, reranking. Raw ANN results are approximate, fast but noisy. You take the top K candidates, say 50 to 100, and run a cross-encoder reranker over them. Cross-encoders are slower but much more accurate because they see both the query and document together. Tools, Cohere rerank, Gina reranker, or open source Colbert. The final output, top 5 to 10 highly relevant, semantically matched results. Section 3, the classic interview question. Design a semantic search system for 100 million documents. Here's how you structure your answer. Step 1, clarify requirements. Is this real-time? What's acceptable latency? Is the corpus static or constantly updated? Multilingual? Step 2, indexing at scale. You can embed 100 documents in a single batch. Use a distributed pipeline, Spark or Flink for parallelism. Embed in microbatches. Use a queue, Kafka, to handle updates incrementally. Estimate costs. At $0.00013 per 1K tokens with OpenAI, 100 short docs might cost $2,000 to $10,000 to embed from scratch. Budget accordingly. Step 3, vector storage. At 100 vectors with 1536 dimensions, float 32, that's roughly 600 gigabytes of raw vector data. You need a distributed vector DB with Chardang, Grant, or Weaviate handle this well. Or use Face with IVFPQ quantization to compress 600 gigabytes down to under 50 gigabytes with minimal quality loss. Step 4, serving layer. A stateless query service, multiple replicas behind a load balancer, embeds queries and fires ANN lookups. Cache popular queries. Semantic search results don't change unless the corpus changes. Redis TTL cache on query embeddings saves 30 to 50% of embedding API costs in practice. Step 5, reranking. Apply cross-encoder only on the final candidates. Don't re-rank 100 results every request. It kills latency. Top 50 candidates, re-rank to top 10. Respond in under 200 milliseconds total. Section 4. Gotchas that senior engineers know. Embedding model drift. If you update your embedding model, all existing vectors become invalid. They're in a different space. Solution, blue-green index migration. Build the new index in parallel, cut over atomically, retire the old one. Never update an embedding model in place. Hybrid search. Pure semantic search misses exact matches. Error code E404. XJ9 has no semantic meaning. Production systems use hybrid. Semantic score plus BM25 score, merged with reciprocal rank fusion or a learned ranker. Always mention hybrid search in interviews. It shows you've thought about real-world edge cases. Cold start on new content. Documents added to the corpus must be embedded and indexed before they're searchable. 4 near real-time requirements. This pipeline must run in under 30 seconds. Async event-driven indexing via Kafka ensures updates propagate quickly. Query latency budget. In a user-facing product, you have maybe 200 milliseconds total. Embedding a query, 20 to 50 milliseconds. ANN lookup, 5 to 20 milliseconds. Reranking 50 docs, 80 to 120 milliseconds. That's tight. Cache query embeddings aggressively. Pre-warm your ANN index in memory. Use smaller, faster embedding models, like BGE Small, for queries while using a larger model for document indexing. A technique called asymmetric embedding. Section 5. How to answer in an interview. The framework. When you get a semantic search question, use this structure. First, define. Semantic search uses dense vector embeddings to match meaning rather than keywords. Second, architect. Talk through indexing, ANN retrieval, and re-ranking, the 3 layers. Third, scale. Address the specific scale requirements they gave you. Mention distributed pipelines, quantization, sharding. Fourth, gotchas. Bring up embedding drift, hybrid search, and latency budgeting. This is where you separate senior-level thinking from mid-level. Fifth, trade-off FS. Cost versus quality. Speed versus accuracy. Open source model versus managed API. Always frame your decisions as trade-offs, not just choices. Section 6. Quick flashcard review. Embedding model converts text to dense vectors. ANN, approximate nearest neighbor, fast vector similarity search. HNSW, the standard ANN algorithm. Logarithmic query time. Cross-encoder reranker, slow but accurate, used on final candidates. Hybrid search, semantic plus BM25 combined via reciprocal rank fusion. Embedding drift, when you change models, all vectors become stale. Asymmetric embedding, different models for queries versus documents. That's your episode 45 deep dive on semantic search at scale. If this helped, subscribe to Agentic AI World. We drop a new episode every day covering the AI engineering topics that matter in senior interviews. Next episode, AI latency optimization. How senior engineers build sub-100 ms AI APIs. See you tomorrow. Keep building.